Welcome back to our explainer series, How Algorithms Actually Think. Now, if you caught our last explainer, you know we went pretty deep into the world of recursion. We looked at how functions call themselves to solve things like factorials or the Fibonacci sequence. And, it's this incredibly elegant, beautiful way to write code. But today we're going to look at the dark side of all that elegance. So let's jump right in.
So here's the hidden problem with those naive recursive solutions we looked at before. What if recursion is just doing the exact same work over and over again? A lot of times, these functions end up solving the exact same subproblem repeatedly, completely blind to the fact that, hey, they've already done this work. They literally don't remember the answer. They just obediently recalculate the whole thing from scratch every single time.
Think about it kind of like this. Imagine you're redoing the exact same complicated math homework problem like 5 times, simply because you forgot you already solved it on another piece of paper. It's wildly inefficient, right? Well, that's exactly what naive recursion does. And the fix for this hidden inefficiency is the entire focus of today's explainer, dynamic programming. Or honestly, you can just think of it quite simply as recursion with a memory.
All right, part 1, the core of DP. Let's break dynamic programming down into some clear, logical steps.
So, what exactly is dynamic programming? Basically, it's an optimization technique used to solve complex problems by breaking them down into smaller, overlapping subproblems. And there are 2 absolutely crucial characteristics to notice here. First, overlapping subproblems, which just means the exact same smaller problems show up multiple times. Second, optimal substructure. This means you can actually use the optimal results of those smaller subproblems to build the best optimal result for the big problem. The whole core idea here is that we solve each subproblem only once, and then we store that optimal result so we never have to do the math again.
Okay, let's use the Fibonacci sequence as our main example here. Just take a look at this top-down branching tree. Let's say we're trying to find the 5th Fibonacci number. To find f of 5, the program recursively calls f of 4 and f of 3. But look really closely at what happens under f of 4. It calls f of 3 and f of 2. Wait a second, we are already calculating f of 3 again. In fact, just to find f of 5, the computer ends up calculating f of 2 3 separate times completely from scratch. And as the input number gets bigger, oh man, this recursion tree just totally explodes. The time complexity becomes exponential. That's big O of 2 to the power of n. Even for an input as small as 30, the computer is suddenly doing around 1 billion repeated computations. The wasted effort is just massive.
And this perfectly sets up our first dynamic programming fix, memoization. It sounds like memorization, and it actually comes from memorandum, meaning to remember. We keep the exact same top-down recursive structure, but we add a memory cache, usually something like an array or a hash map. So the very first time we calculate f of 3, we drop that answer right into our cache. Then later, when the recursive tree branches out and asks for f of 3 again, our algorithm stops. It checks the cache, finds the answer sitting right there, and instantly returns it. We literally prune those massive duplicate branches right off the tree. What used to take a super slow exponential time suddenly drops to a fast linear time, or O of n.
But dynamic programming actually gives us a second way to tackle this, and it's called tabulation. Instead of starting all the way at the top and recursively drilling down, tabulation says, hey, let's just start at the absolute bottom. We totally ditch the recursion, we set up a simple table or an array, and we just iteratively build the solution from the smallest values upward.
Just look at this grid. We already know our base cases for Fibonacci, right? Index 0 is 0, and index 1 is 1. So we just fill those in. Then we use a simple loop. To find index 2, we just look back at the previous 2 cells we already filled out. 0 plus 1 is 1. For index 3, we add index 1 and 2, which gives us 2. We literally just march left to right, filling in one single cell at a time until we hit our target. Every step perfectly builds toward the final answer using the previously filled cells, and we do it all without a single recursive call.
So the really crucial point here is understanding when to use which approach. Memoization is often a bit easier to write because, hey, if you already have a recursive function, you basically just slap a cache on top of it. Plus, it only computes the specific subproblems it absolutely needs. But, and this is a big but, because it relies on recursion, giving it huge inputs can actually cause a stack overflow error in your computer's memory. Tabulation, on the other hand, requires you to think iteratively from the bottom up, which can sometimes be a bit trickier to set up for really complex problems. But because it avoids the recursive call stack entirely, it's generally a lot faster and way safer for your memory.
All right, part 2, DP in the real world. Let's step away from all the abstract math for a second and see where this actually shows up in practice.
You might not realize it, but dynamic programming is the hidden engine inside a ton of the technology we use every single day. Pathfinding and route planning tools, like that navigation app sitting on your phone right now, they use DP to find the shortest distance to your destination by building on the shortest paths of intermediate steps. It's used heavily in the logistics industry for allocating resources. It's even used in genetics for sequence alignment, basically figuring out how to transform one DNA sequence into another with the lowest possible cost. And structurally, the whole DP idea of cache the answer so you never recompute it is the exact same fundamental principle powering massive databases and web servers all across the globe.
Oh, and I absolutely have to mention this for the career-minded folks watching. Dynamic programming is widely considered the ultimate gatekeeper in software engineering interviews. Tech companies heavily test this concept because it proves you can take a brutally slow, inefficient algorithm and actually optimize it to run elegantly at scale. Moving on to part 3, common DP misconceptions. Because dynamic programming has such a, daunting reputation, a lot of myths have sprung up around it. Let's clear those up right now.
Myth number 1 is that dynamic programming is this totally alien, magically disconnected thing that requires you to learn an entirely new paradigm. The reality is much friendlier. As we saw with memoization, DP is built directly on top of recursion. Honestly, if you understand how a function calls itself, you already understand the hard part. DP is really just recursion with a little notepad to jot down your answers along the way.
Which naturally brings us to the inverse myth that dynamic programming always must use recursion. Actually, scratch that, it's not true at all. Remember our tabulation grid from earlier? We calculated that 5th Fibonacci number using nothing but a basic iterative loop, building straight from the bottom up. Tabulation is a pure dynamic programming approach, and it bypasses the recursive call stack completely. No recursion required.
And the third big myth is that DP is some kind of magic bullet that can fix any slow algorithm. Time for a reality check. DP only works if the problem has those 2 specific traits we discussed earlier, overlapping subproblems and optimal substructure. If you're looking at something like merge sort, which uses a non-overlapping divide and conquer tactic, the subproblems don't overlap. You're sorting completely different halves of an array, so there is literally no reason to cache the answers. Basically, DP is a precision tool, it's not a universal hammer.
Part 4. Why this concept matters. Let's zoom out a bit and synthesize everything we've learned today, and look at why adding this to your mental toolkit is such a massive leap forward.
There's this great quote that sums it up perfectly. DP is literally the technique of taking an exponential, slow solution and turning it into a fast, practical one. Dynamic programming is easily one of the highest leverage concepts in our entire Explainer series because it is the exact bridge where everything comes together. You take the beautiful structural elegance of recursion, you analyze the horrible exponential big O notation it creates, and then you apply DP to collapse it into a lightning-fast, practical solution. It is the ultimate manifestation of thinking like an engineer, identifying redundant work, and engineering your system so it never does that work twice.
And finally, part 5, the tech canvas closing. Let's tie this back into the broader journey we've been on together.
Looking at our timeline for the How Algorithms Actually Think series, you can see how everything has been building straight to this moment. We started out with the basics of recursion, then we explored backtracking and divide and conquer, we learned exactly how to measure efficiency with big O notation, and now we've conquered dynamic programming. You now possess the foundational mental models to really understand optimal algorithmic thinking.
But hey, our journey definitely doesn't stop here. Alongside our ongoing algorithm series, we're going to start exploring some deep dives into software engineering architecture, career navigation, and even the fascinating history of tech that shapes our world today. I seriously can't wait to share it all with you. Until then, I want you to ask yourself a question. What complex, repeating problems in your own code, or honestly, even in your own life, could be solved if you just stopped for a second to write down the answers? Thank you for watching The Tech Canvas. Complex ideas, clear pictures. Follow for more.